Hello students, I welcome you all in our lecture second, which is based on the topic Basics of Chemical Kinetics. So in the today's lecture we are going to learn some numericals based on rate and stoichiometric coefficients, their relation. The next point that we are going to see rate law and units of the rate constant for various order reaction. That means we are going to study the unit of rate constant for the first order, zero order, second order and the various order of the reaction. The next part we are going to see integrated rate law of zero order reaction. In the previous lecture, we have seen the reaction rate and stoichiometry. In that, we have basically taken an example that AA plus BB gives CC plus DD as a product. And we relate these reactant terms and product terms to the rate, where rate is equal to minus 1 upon A, change in concentration of A with respect to time. Here minus is there because it is the reactant, and reactant get consumed or the concentration of reactant gets decreases. That's why that minus sign is there. So whenever there is a reactant, you have to write the minus sign. So 1 upon B, change in concentration of B upon change in time, equal to, when there is a product term, we write plus. So 1 upon C, change in concentration of C with respect to change in time, which is equal to 1 upon D, change in concentration of D with respect to time. Okay. So here I will take one example that Hg plus Cl2 gives HgCl2. Okay. So now we will write rate is equal to, so now here reactant is Hg, 1 upon 1 is 1, minus, why minus? It is in the reactant side. Change in concentration of Hg upon change in time, which is equal to minus change in concentration of Cl2 upon change in time, which is equal to plus change in concentration of HgCl2 with respect to change in time. So now again I will take another example. 2Hi gives H2 plus I2. Okay. So now for this reaction, rate will be equal to minus, for the reactant side, here stoichiometric coefficient is 2. So 1 upon 2. Change in concentration of Hi upon change in time. Okay. Which will be equal to 1 upon 1 is 1. Change in concentration of H2 upon change in time. I2 change in time. So here we will solve an example related to this. So here the question is, for the reaction 2x plus y gives z, the rate of reaction appearance of z is 0.05 moles per liter per minute. The rate of disappearance of x will be, so first of all what we will do, we will write the reaction. The reaction is 2x plus y gives z. So now for this reaction, rate will be equal to minus 1 upon 2 dx upon dt, which will be equal to minus 1 upon 1 is 1 dy upon dt, which is equal to plus dz upon dt. Okay. So in the question, what is given? Appearance of z, that means dz upon dt, and which is equal to 0.05 mole per liter per minute. Okay. And what you have asked to find? The question is, the rate of disappearance of x will be. So what you have to find? Dx upon dt you have to find. But we know the relation that minus 1 upon 2 dx upon dt is equal to, we are relating this to dz upon dt. Okay. So now, keeping this as it is, minus dx upon dt 2 into the value of this we know, that is 0.05 mole per liter per minute. Okay. So therefore the rate of disappearance of x will be equal to 0.1 mole per liter per minute. The another question is, if the formation of SO3 in contact process, that is 2SO2 plus O2 gives twice SO3, the rate is expressed as minus d concentration of O2 upon dt is equal to 2.5 into 10 raised to minus 4 mole per liter per minute. The rate of disappearance of SO2 will be. So first we will write the reaction 2SO2 plus O2 gives twice SO3. Okay. So now what is given to us? Minus dO2 upon dt is equal to 2.5 into 10 raised to minus 4 mole per liter per minute. We know that rate is equal to minus 1 upon 2 change in concentration of SO2 upon change in time is equal to minus dO2 upon dt, which is equal to plus 1 upon 2 change in concentration of SO3 upon dt. Okay. So now what we have to do? We have to relate these two. That is minus 1 upon 2 dSO2 upon dt is equal to minus dO2 upon dt. Okay. So now the rate of disappearance of O2, that is minus concentration of SO2 upon dt is equal to 2 into the value of this is 2.5 into 10 raised to minus 4 mole per liter per minute, which is equal to 5 into 10 raised to minus 4 mole per liter per minute. Okay. So these are very basic questions, but these are most important, which are asked in all the types of competitive exams in the chemistry. The next that we are going to see is rate law. So the reaction rate is expressed in the terms of rate law. It is also known as a empirical rate law. So what is the meaning of empirical? Here empiricals mean experimental. That means the reaction rate are expressed in terms of concentration is known as a rate law, and the empirical rate law indicates that it is derived from the experiment. That means rate law is derived from the experiment. That means it is a experimental quantity. So here we will take one example that AA plus BB gives CC plus DD. Okay. So when in the rate law, rate is expressed in the terms of concentration of reactant. Okay. In the rate law, the rate is expressed in the terms of concentration of reactant. So when we remove this proportionality sign, we introduce the new constant, that is K. And here the reactants are A and B raised to some exponent. Okay. So this K is known as rate constant. It is also known as proportionality constant. It is also known as a velocity constant. Okay, and this X and Y are order with respect to reactant A and B respectively. That means X is order with respect to reactant A and Y is order with respect to the reactant B. So now X and Y are not equal to A and B. That means the order with respect to the respective reactants are not equal to their respective stoichiometric coefficient. The stoichiometric coefficients are the different terms and the order are the different. Sometimes they may be same, but they are not equal at all. So overall order of reaction is equal to X plus Y. So the sum of order of respective reactant expressed in a rate law is the overall order of the reaction. Is it clear to you now? The next we will see the units. So now we know that rate is equal to K concentration of A raised to X, concentration of B raised to Y. Okay. So now we know that rate is equal to change in concentration of reactant or product. Okay, upon change in time. Okay, so here there is a concentration versus or concentration upon time. Okay, so the unit of rate is always mole per liter per minute or mole per dm cube per minute or whatever, but it is the change in concentration upon time. But the unit of rate constant always changes. Okay, it always gets change for each and every order of the reaction. So here we know that rate is expressed in concentration upon time, which is equal to K into, this is a concentration term, raised to X into concentration term raised to Y. Okay, so which will be equal to K to concentration raised to Q, where Q is X plus Y, that is the order of the reaction. So therefore K is equal to concentration raised to 1 minus Q per time. Okay, per time. So for zero order reaction, Q is equal to 0. So now putting this K concentration raised to 1 minus 0 time. So the unit will be mole per liter raised to 1 time, that is expressed in second. So the unit will be mole per liter per second. Okay. Now for first order reaction, for first order Q will be equal to 1. So K equal to mole per liter 1 minus Q, that is minus 1 time inverse. Okay, so minus 1 is 0 time inverse, that is per second. Anything raised to 0 is 1. So from this you can derive the unit of rate constant of any order of the reaction. Here we will take for the second order. For second order, Q is equal to 2, K will be equal to mole per liter 1 minus 2 per second. So this mole per liter is raised to minus 1. So therefore it will be per mole liter per second. Okay. So you can find the unit of rate constant for third order, for fourth order and also for the fifth order by using this formula. The next is molecularity. of reaction. So this you have studied in the previous classes, that order and molecularity. Molecularity is theoretical quantity. It is a theoretical quantity, okay? So when the reaction is like this, A gives the product B, then it is a unimolecular reaction. Okay? If the reaction is like this, A plus B gives the product, it is a bimolecular reaction. If the reaction is like this, A plus B plus C gives P, then it is said to be trimolecular reaction. So molecularity is a theoretical quantity and which can be determined from the reaction. Okay. The next we will see integrated rate law. So this we will see for the first zero order reaction. Okay. So now for the zero order reaction, that is R gives the product P. Okay. So now we know that rate is equal to minus D concentration of R upon dt. Okay. Which is equal to K into concentration of R. So the order is zero order reaction raised to 0. Okay. Now we will take this both, that is minus change in concentration of R with respect to time is equal to K into R raised to 0. Okay. So now we will shift this term minus dr upon dt is equal to K, and thing raised to 0 is 1. K into 1 is K. So now minus dr is equal to K dt. So here dt is in the denominator, that means in the division side. When it moves towards to another side of equal, it becomes multiplication. Okay. So next is integrating on both the sides. Okay. So now integration minus D concentration of R. So R from R0 to RT, where R0 is the initial concentration of reactant and RT is the concentration of reactant at time T, which is equal to integration K dt. So from 0 to T. Okay. So the next is integration of minus dr is R, and the limit is from R0 to RT. Okay. Which is equal to K is constant, K will come outside, integration of dt is T, and T from 0 to T. Okay. Now putting this limit, upper limit minus lower, RT minus R0 is equal to KT. Okay. So here K is equal to 1 upon T here there is a minus sign outward. So now merging this minus sign, that will become R0 minus RT is equal to KT. Okay. So therefore K is equal to 1 upon T R0 minus RT. Okay. So this is the integrated rate law for the zero order reaction. Okay. So now we will study some graph for this. So the graph of time versus, or we can write graph of concentration of reactant at time t versus time. So now we will rearrange this equation in the form of y is equal to mx plus c. Okay. So y is RT. So what we will do? We will take this KT. KT is equal to R0 minus RT. Okay. So we can rearrange this. We will take this at this plus RT, which is equal to minus KT plus concentration of R0. So now this is a y, this is mx plus c. So here y is RT, that means we will take on y axis concentration of R, that is reactant at time t versus time. So this will be straight line with negative slope, that means like this, but having some intercept. So this graph will be like this. So this intercept will be equal to R0 and slope will be equal to minus K. Okay. If we will take the graph of we will take the graph of rate versus concentration, it will be straight line. Why? We know that rate will be equal to K into concentration of R raised to 0. That means K. So rate is constant. It does not depends on the concentration. This is the most important for the zero order reaction. So here we will stop now. Thank you.